Welcome to Shapers Learning Academy, Deep Learning Module number 8. In the previous module, we did learn about convolutional neural networks and its details. In module number 8, you will get to learn about the data and batches, hyperparameters, fine-tuning, batch normalization, vanishing and exploding gradients. Happy learning. What are hyperparameters? Hyperparameters are the variables which determine the network structure, similar to the features of a neural network. Hyperparameters are set before training, before optimizing the weights and bias. The third element is mini-batch gradient descent. As you may know, gradient descent, the objective of any gradient descent is to optimize the neural network in order to have the proper and perfect predictions. So mini-batch gradient descent, which is normally the type of gradient descent algorithm used by most neural network, in which a gradient update will occur per batch basis. More about batches and normalizations in the further slides. Next, fine-tuning and transfer learning. As we know, we are in the phase of narrow AI experimentations, where we are in the process of training various neural networks for various applications around the world. So fine-tuning and transfer learning are the concepts which will help us to not reinvent the wheel. I mean to say that this fine-tuning and transfer learning concepts can be used to reuse the neural network, the parts of neural networks while building new neural networks. So transfer learning occurs when we use knowledge that was gained from solving one problem and apply it to a new but related problem. Whereas fine-tuning is a process that takes a module that has already been trained for one given task and then tunes or tweaks the model to make it perform a similar second task. Now, why to fine-tune? Assuming the original task is similar to the new task, using an artificial neural network that has already been designed and trained allows us to take the advantages of what the model has already learned without having to develop it from the scratch. To give a detailed example, imagine that we have a neural network which has been designed to predict cars. So the same neural network cannot be used to predict trucks, but with certain changes and reuse and fine-tuning, we can use a neural network which predicted cars to predict trucks. Hence, this reduces a big time in the training process. Let's come to an interesting concept called as batch normalization. What is normalization? Normalization in mathematics or general terms can be defined as transforming the data you are working with to a common frame of reference. When the data is spiked, when the data is biased, when you bring the data to a common frame of reference, we call that as normalization. How does normalization is done in the usual sense? A typical normalization process consists of scaling numerical data down to be on a scale from 0 to 1. See, there are various normalization functions which will transform your data between 0 to 1. And typical standardization process consists of subtracting the mean of the data set from each data point, then dividing the difference by the data set's standard deviation. So, how do you think this normalization will help neural networks? Yes, it has a great advantages. As we know that neural network works on data or the training set. The training set is the fuel. When we have spiked and biased data in the training set, the training process as well as the learning rate as well as the predictions go wrong or go awry. So it is better to normalize the data in batches in order to have better predictions and better efficient neural networks. Batch normalization and neural network. So why that would be required? The larger data points in these non-normalized data sets can cause instability in neural networks because the relatively large inputs can cascade down through the layers in the networks, which may cause imbalance gradients. Imbalance in non-normalized data may cause problems with a network that make it drastically harder to train. We may recall that activation function is itself a normalization function. So our inputs along with the weights is passed on to an activation function, right? The product of our input as well as the weights. When we pass it, our activation function actually makes a normalization process, and hence an activation function is a normalizer. When applying batch normalization to a layer, the first thing the batch normalization does is normalize the output from the activation function. This addition of batch normalization to a model can greatly increase the speed in which training occurs and reduce the ability of outlying large weights to over-influence the training process. Let's understand a problem called as vanishing gradient problem. So before getting out of the problem or the theory, let's recap certain concepts. We know about a forward pass or an epoch. An epoch or a forward pass is a complete travel of data through all the layers of the network. So once the data travels through all the neurons or all the layers of the network, obviously the loss is being calculated by the SGD, stochastic gradient descent, and with the loss calculated at the gradient, the previous weights are being updated again. So this is the process of actually making the neural network more efficient. So with this education, let's understand, or with this recap of this education, let's understand this vanishing gradient problem. So during training, stochastic gradient descent works to calculate the gradient of the loss with respect to the weights in the network. Gradient with respect to weights in the earlier layers of the network sometimes becomes really very small, vanishingly small. Hence this is called as vanishing gradient. When the gradient is really small, there will be actually no change or no update. As a result, this weight becomes a kind of stuck, never really updating enough, and impairs the ability of the network to learn well. Now imagine the same problem in the opposite direction. There we encounter this exploding gradient problem. Think about calculating the gradient with respect to the same weight, but instead of really small terms, what if they are really large? Larger the gradient is going to be, thus essentially exploding the size. Instead of barely moving our weight with this update, we are going to greatly move it. So much so that the optimal weight of this weight won't be achieved because the proportion to which the weight becomes updated with each epoch is too large and continues to move further and further away from its optimal value. Keeping it short, the objective of any neural network is to optimize the weight, and in order to achieve that optimal value, the network relearns, updates its weight again and again. Sometimes the gradient value is so small that the previous weights are either not updated, which is the vanishing gradient problem, or sometimes it is so large that it explodes, sometimes beyond the normalized values, beyond 0 to 1. In both the cases, the further updations to the layers are really complex and will result in an inefficient neural network layer. So it is very important for a designer or a neural network engineer to handle the exploding as well as the vanishing gradient problems. Thanks for your time, thanks for your patience, and thanks for your learning.